All right. Happy Wednesday, everyone. This is the start of International Listening Week. Luckily, we can all observe it with today's webinar, where we'll hear all about radiant floor heating systems. We're going to discuss the short-term and long-term efficiencies that can result from installing a hydronic radiant floor heating system, as well as their installation applications and heat sources. Our presenter today is Steve Swanson, National Trainer at Uponor Academy. He holds more than 46 years of hydronic and steam heating experience and has toured the country speaking and training on the concepts of system operation and design. He helped develop curriculum and training for hydronic heating seminars and also contributed to the training for the State of Minnesota Boilers License. In addition, he holds a Lifetime Achievement Award from the Minnesota Multi-Housing Association for training and curriculum development. He's a certified trainer through IATMO. And finally, he was recently appointed to the advisory board of the Radiant Professionals Association. And during the course of today's presentation, you can submit questions for our guest. Simply use the questions box that should be located on the right side of your screen. I'll review those questions and pose them to Steve during the Q&A time set aside after his presentation. Steve, we're all ready to listen to you.
Well, thanks very much for having me on the show today. It's a good afternoon. The picture that you're looking at right there is a view of Minneapolis skyline, and you notice what's missing is the snow. That's because it's a beautiful 82 degrees here today, and we're glad you could be joining us as we talk about radiant heat. Now, at the onset of this, I do want to say that I am an unabashed and unapologetic wethead. I love hydronic heating. So with my 48 years of experience doing this, 46 years, whatever amount that is, I forget now, that if you're a forced air fan, I hope I don't offend you too much. Having said that, here's what we're going to do today. We're going to talk a little bit about heat, what it is and where it's going, and then what choices do we have today for heating systems, and then a little bit about the benefits of radiant heating, including comfort, indoor air quality, energy savings, and design flexibility. We'll start off just talking about heat just for a minute. So we all know that heat rises, right? Actually, that's a trick question. Heat does not rise, hot air rises. Heat always goes from hot to cold, and it doesn't matter what direction. So if you're standing next to a cold surface, heat will travel from you to the cold surface in an effort to make you both the same temperature. And that's how the heat spectrum works, and that's what we're going to be working with as we talk about how do we make heat comfortable for you to live in. Now again, on this heat travels in three ways: conduction, convection, and radiation, and it always flows from hot to cold. We have conduction, which is the transfer of heat through a solid material. Convection is when we transfer heat by movement of fluids, particularly air. Baseboard heat is a convection heat. Forced air is a convection heat. And then we have radiation, which is the transfer of heat in the form of electromagnetic waves. This is how the Earth is heated by the sun. And a good example of that would be if you've ever been at a campfire on a cold night, you know that the front of you is hot and the back of you is cold. That's radiant heat at work. Now, if you could get the radiant on all sides of you, you wouldn't have a cold spot on you. So that's what we're going to try to do. And so we're going to talk about this effect of radiant heating. Why does it feel colder when you walk down a frozen food aisle? Now, I went with my wife to one of our favorite grocery stores, and I brought with me an electronic thermometer. And I stood in the frozen food section and held up this thermometer, and my wife went dork and turned around and left. But the point being, you know how cold it feels when you're in there, but the actual air temperature was only 1 degree less than the rest of the store, but it felt really cold. Now, why is that? Well, in this case, it's because those freezer cases are at 0 degrees, and my body is at 83 degrees, and the wider the temperature span, the faster the heat flows, and my body picks up on this large heat flow induction and causes me to feel colder. So that's why in your own home, you can feel cold even if you have an air temperature that's set at even 72. So there's different circumstances, not just air temperature, that determine whether you're comfortable. And so we all know, don't we, that heat is leaving our houses, right? So we know that no matter what you set the heat to, if you don't put any more heat in, eventually you're going to get cold. Well, where is this heat going, and why is it leaving? And so if we take the model of this house here, you'll see that heat is leaving your house through a wide variety of places: ceiling fans, dryer vents, anytime there's a penetration in the shell of the home for a faucet, through electrical outlets. If you want a good display of how this works, in the next time it's really cold in the wintertime, take an outside electric outlet that's on an outside wall in your home and hold a match up there. A lot of times the air is coming in there so fast it'll blow the match out. And that's all this cold air coming into your house, and then it's leaving through plumbing vent stacks. Anytime that can find a way out, it's going to go out. So we have to find a way to replace that. Now, when the building industry itself is about business sustainability, not necessarily energy sustainability. Their main job is to make money as a home builder. And I understand that. I'm not picking on them. It's just the fact that they're about business sustainability. And so they have a set of codes that they go by to determine what's the minimum that they can put in a home. And so the building codes do not require comfort or efficiency as a measurement of safety or health. At the bottom line of the codes is, the only rule they want to really enforce is that the building doesn't kill you at the end of the day. So they want to make sure that you're at least safe in your home. But efficiency has little to do with it. And also the building industry typically allows from 3 to 5% of the construction cost for the HVAC system. This would be your heating and cooling plant. At this level, it will provide safety and health, but at a minimum cost. And so we see that the heating code is not at all the same as the comfort code. And so we want to talk about that just a minute. So what different types of heating systems do we have? We'll take a look at those in order of how many of them there are. First one is forced air. In today's market in the United States and North America, 95% of all single-family homes are forced air. And the other 5% is divided among the rest of them. Interestingly enough, in Europe, it's exactly backwards. 95% of the homes are heated with hydronic heat and 5% with forced air. And you'd ask the question, wow, why is that? And part of the answer to that is because in Europe, their gasoline costs $12 a gallon for gas. They simply cannot afford forced air. And many of the codes prohibit forced air installation as an energy-saving alternative. Now, as far as the HVAC part of a forced air part, we have the heating, and the issue with forced air is the problem that I see with it anyway, is what they're heating. They're using air as the way to heat you, and air is one of the worst conductors of heat that there is. And so when you, for example, when you want to make insulation, don't you trap air in something, and that's what makes insulation? When you want to make windows better, you trap air between panes of glass. Well, air is an insulator. Why would we be using that as a means to transport heat from one place to the other? So that's part of the question. And so you end up, because hot air rises, you end up with stratification where the floor is colder than the ceiling, temperature drift, drafts, noisy fans, those kind of things. Sometimes you have to turn the TV up a couple clicks when the fan comes on, that kind of thing. The next part, the ventilation part, the EPA says currently today, air pollution inside of homes is typically 5 times higher than the outside. Now, that's got to leave us something to think about. But in a budget of 3 to 5% of your building costs, you probably are not going to get the best ventilating system that you can get. And you'll get exhaust fans in your bathroom and kitchen, but probably not much else to take out dust and mold and particles and that type of thing. And as for air infiltration, when you buy a typical inexpensive forced air furnace, you're going to get a disposable fiberglass filter that doesn't meet a single healthcare facility standard. It'll filter some dirt and dust, but none of the microbial issues or harmful gases that are passed around are trapped by them. Professor Lee of the University of California said, these filters protect the health of the blower motor, not the body at the end of the day. And the other thing that we see right away is it doesn't heat the domestic water either. So you have to provide another means to heat your domestic water. And typically those aren't very efficient. So we have issues with those as well. So that's forced air. The next one is hydronic heating. That's anything, thanks to Bell and Gossett for this drawing. I forgot to put a little thank you to them. Hydronic heating typically is divided up into 3 separate areas, but these include anything that are heated with water, which would include baseboard heat, radiator, and radiant heat. Now, baseboard heat is still convection heating. Radiators are about 50% radiant heat and 50% convected heat, and then radiant heat in cement or concrete would be about 95% radiant heat and 5% convected heat. And that's the types of hydronic heating we have. We also have today electric heating, which is the least expensive to install and the only one that's 100% efficient, but to run it is extremely expensive. You can sit outside and watch your meter spin right off the dial there. Along with that, we have geothermal heating, which according to, and these are typically attached to a radiant heating system. The Environmental Protection Agency says that this is the most cost-effective means of heating a house today. Now, it might be more expensive, but it is very cost-effective to run. Solar heating is also available out there if you have the right conditions and the right amount of sunshine. It's a little bit expensive to install and those types of things. And if your neighbor builds an oak tree that happens to go over the top of your solar collector, then you lose a little bit of your heating there. So now all of these things will replace the heat that's in your house, but that does not guarantee that you'll be comfortable. So I want to talk just a second about comfort. Isn't that doesn't that look great? That's a great inviting comfort shot, I thought. And I have a really good quote from friend Mark Eaton, who talks about what the definition of comfort is, and I really like this one. It says, not being aware of your environmental surroundings. You're not hot, you're not cold, your sinuses are not dry, nor is the humidity too high. You shouldn't be able to hear any noises associated with the delivery of your comfort. If you're not thinking about your surroundings, simply stated, you're comfortable. Isn't that a good definition? Thanks, Mark. I really do like that one. And part of the situation about us as we understand comfort is we have to know that our body is a little HVAC system, a little heating, ventilating, air conditioning system all built into one, and not a very good one either, I might add. And so we manufacture about 500 BTUs per hour just sitting there. Each person does, not moving or anything, just sitting there. Of the 500, 100 of it is used to metabolize your food. The other 400 of it is cast off from you. And your body, for all of the sensors are out there, you have about 250,000 temperature sensors on your body. None of them are able to measure the temperature. The only thing they can measure is how fast or slow heat is leaving you. The faster it's leaving you, the colder you feel. The slower it's leaving you, the warmer you feel. And it will adjust itself to those. It doesn't know how hot it is. It can only tell how fast it's leaving. And I'll give you an example of that. If you'll take a second and just wherever you're sitting, take your hand and put it on the table. Okay, go ahead now. I know, just make sure you do this now. Now tell me, does it feel hotter or colder than the air around you? And most of you will say, well, it feels colder. But you know it can't be colder. It's sitting in the same room. It should feel the same. but conduction carries heat so much faster that your body feels this is colder even if it isn't colder. So that's an important thing for us to understand in the comfort pie. So we lose about 50% of our body heat through radiation, 20% through evaporation, and another 30% through convection. It just kind of bubbles out from you. And so when you're in an environment, radiant heat, remember, will go any direction. So if you have tables that are colder than you or surfaces that are colder than you, like, you know, that granite countertop you have in the kitchen that's always colder than the rest of you, that's why your body's radiant heating to try to heat that big slab of granite up. So now we're going to talk just a little bit about the differences between forced air and radiant as a way to replace the heat. Because forced air uses air, heated air, as a convection form of heating, it will come into a room, and because hot air rises, typically the hot air will rise up towards the ceiling and the cold air will settle back down to the floor. It'll create a circulation path, and that's the temperature. So you can see from the drawing here that there's quite a variety of temperature from the floor to the ceiling, and that's one of the temperature differences that we were talking about. On the right, you see that what a radiant system that has in-floor radiant heating, you'll find a much leveler path of heat, and the best news is the heat is where I want it to be the most, which is where my feet are. Most of you have cold feet walking around your house. So this is a drawing that's been out for quite a few years. It started way back in the 1950s when the National Energy Association came up and wanted to find out what makes people comfortable. And they came up, they literally tested thousands of people and found that the ideal heating curve, your feet are around 73 to 75 degrees. Up near your heart is around 65 degrees. And then it tapers off after that because you don't need the heat up there. Unless somebody's paying rent up there, you don't need heat up in your ceiling. And so you see on the left, you'll see the black line represents the ideal heating curve. However, the blue line represents the actual heating curve. Since hot air rises, you have 63 degrees at your feet and about 90 degrees up at the ceiling. So all my heat is now up at the ceiling. And you can see my feet feel colder than they are. So I want to get my heat back, so what do I do to get my heat back? Well, I put a ceiling fan in so I can blow the hot air back down on my cold feet. Well, now I've just created a draft to get my own heat back. And that's why you'll find that sometimes stratification inside of a room can be make it uncomfortable to be in, even though the temperature on the thermostat says that you should be comfortable. On the right, you see where the ideal heating curve and the radiant heating curve are almost identical to one another. That is 73 degrees down by your toes. You have nice toasty toes. Oh, that feels so nice in the winter. Unfortunately, my wife and I built our house back in the 70s when they didn't have radiant, wasn't particularly available. So we have a forced air home, but I've been in hundreds and hundreds of radiant homes, obviously. And there's nothing like it in the wintertime. Once you have it, it's just hard not to have it. So where is the heat? So on the left, you see the forced air. On the right, you see the radiant. And relative to the thermostat in a forced air home, relative to the thermostat, most of the heat is above the thermostat. Well, nobody's living up there. Versus the radiant system, where relative to the thermostat, most of the heat is below where I'm living. That explains one of the reasons that radiant heating is so incredibly comfortable, which explains this part right here. What does every house with forced air heating have in common? They all have a blanket on the couch. Now, test me on this, tell me I'm wrong. But every forced air house I've ever been in has a blanket on the couch. Why? Because the temperature down at that area is cooler and you feel colder. So what we'd like to do is take our radiant heating system and heat up the couch and let the couch heat you up. Therefore, you don't need the blanket anymore. So as we look at it, how important is air temperature as a measurement of the comfort that you're in? How important do you think that is? And when we talk about air temperature, it's just this exactly as the name implies. It's the temperature of the air alone, just what it says it is. It's not the true impact of what you're feeling inside of you. It's not a measurement of true temperature. Now, we have to add another thing to that called mean radiant temperature. Since we lose 50% of our heat radiantly, we'll need, if we're going to measure temperature correctly, we're going to need to know what's the average surface temperature of all of the pieces of furniture and walls and flooring inside of a room. That's called mean radiant temperature. Now, there are thermostats today that can measure mean radiant temperature in a room, and what they do is they'll take the mean radiant temperature, add it to the air temperature, divide it by 2, and then you get something called operative temperature, which is the true measurement of what you're feeling for temperature inside of a room. So let me give you an example. Suppose I have an air temperature of 72 degrees and I have a mean radiant temperature of 64 degrees with all the furniture in the room. If I add those two up and divide it by 2, I'll get 68 degrees. That's what it'll feel like to my body. Now, if I take the air temperature of 64 and make the mean radiant temperature 72, add those two up, divide it by 2, I'll get 68 degrees. I'll feel exactly the same, even though I've dropped the thermostat 6 degrees. There's absolutely no difference in the way that I feel. And this is exactly how a radiant system works versus forced air. What you see on the screen, the top 2 numbers are typical forced air numbers, and the bottom 2 numbers are typical radiant numbers. So that's part of the picture of energy savings, and one of the reasons that your feet feel so comfortable. So another question you ask if you have forced air, how many thermostats do you have in your house? Now, my house, again, is a 3-story house. I have a basement, 1st floor, 2nd floor, and we have 1 thermostat, and it's in the hallway where no one lives. So that's important. My car has 3 thermostats: driver, passenger, back seat. My house has 1. Something's wrong there. And I don't know how you folks are, but my wife and I are like wildebeest. We migrate twice a year, just like the wildebeest do in Africa. In the summertime, we have to migrate upstairs or downstairs because it's too hot upstairs. And then in the wintertime, we have to migrate upstairs because it's too cold downstairs. So twice a year, we migrate, just like the wildebeest. And I'm saying if this is my castle, I should be comfortable everywhere I go in there. So with that in mind, I want to talk just for a minute about indoor environment quality. This is what the engineers at ASHRAE have determined. This is what makes you comfortable and environmentally. We start off with indoor air quality. This is the volatile organic compounds, the formaldehydes, the adhesives, the solvents, the propellants that you shoot out of your hairspray. All of that is a part of the indoor air quality. Microbial contaminants such as mold and bacteria, Legionella, gases such as carbon monoxide and radon are all part of this quotient. Pesticides, glues, asbestos all fall into this category as well. Next to that, you have the indoor comfort quality. Now this would include operative temperature, relative humidity, asymmetrical temperatures, like when you walk next to a picture window in the middle of winter, you know how cold that feels. Temperature drift, stratification, the difference between the ceiling and the floor, those are all part of the indoor comfort quotient. So you can see you could be quite comfortable in the basement in the summertime, so your comfort quality is fine, but if there's radon leaching out of the walls, then it doesn't meet the indoor air quality quotient, you see? So you want to have all 5 wheels. Picture a wheel with 5 spokes. If any one of the spokes is out of balance, the wheel's going to go thump, thump, thump down the road, and so will your environmental quality. The next one is indoor sound quality. These are fan noises, air velocity, vibrations from equipment, humming noises that you can't explain, outdoor noises transmitted through thin glass, that type of thing. The fourth one is indoor light quality. The National Research Council has determined that effects of indoor lighting also affect how you feel comfortable as your circadian system kicks in to fight depression. So lighting could actually affect the mood that you're in your house, seasonal affective disorders, and your sleep as well. And finally, the last one is indoor odor quality, where you cooking odors, you know what it's like to cook lutefisk down there in the kitchen, and then there goes the bedroom for that. And so you have, any of you had lutefisk, by the way? That stuff is terrible. Indoor air quality could cooking noises, paint, mustiness, and then you combine that with the air filtration performance of most fan or filters that are paper filters that are in furnaces, and you don't really have much of an indoor air quotient in there. And so you wrap all of this up together and you have your indoor environment quality. Now take a look at that just for a minute, and of the five, how many of them, of the five, are directly affected by your heating system? I would say that 4 of the 5 things that affect your comfort inside your environmental quality inside of your home are directly affected by your heating system. So if you want to feel comfortable in your home, that heating system is a huge part of it. And I want to talk about this infiltration just for a minute longer. I would imagine many of you who have forced air also have carpeting on your floors, correct? And most of the time we have carpeting. Why? Because your feet are cold, because all your heat's up at the ceiling. So we put carpeting on the floor to keep your feet from feeling cold. I want to talk just a minute about this carpeting that's on a floor. Now, if any of you have weak stomachs, you may want to turn away just for a minute. But if you only knew what was inside of carpeting, go online and you can look it up yourself. Carpeting doubles its weight in 7 years. No matter how much you clean it, it doubles its weight, because you can vacuum and vacuum as much as you want, but you're not going to pick up all the dirt or all the rest that's in there. Now, I also want you to know that every human being sheds about 1.5 million skin cells every hour. Within 24 hours, you completely shed the outside of your skin and rebuild a new one every single day. So you're shedding about 1.5 million skin cells every single hour. And where do you think most of those are going? Well, they're going one of 2 places. They're either going in the carpeting or being sucked up into the forced air system to be circulated around the house. And most of you know, when you start your furnace up in the fall, that terrible odor that you get, that's skin cells on the heat exchanger burning. So the last time your Uncle Harry was over and left a couple of 100 million skin cells around, that's what you're smelling. That's disgusting. Now, as if the dead skin cells weren't enough, guess what feeds on the skin cells? Dust mites. Dust mites, they hatch, reproduce, and die within about 3 weeks. And on 10 square feet of carpeting, an average of 10,000 live dust mites will live. And I don't care how much you clean it, they'll still be there. 10,000 dust mites. In this same area, 10 square feet, you'll probably find another 100,000 dust mite carcasses that are busy decomposing in your carpeting. And the fecal matter and the decomposing bodies produce serious health implications. People have found out they're allergic to all of these dust mites and all that fecal stuff that comes off from them. When they remove their carpeting, a lot of the allergies go away. And people who have allergies, usually the allergist will tell them first thing, remove the carpeting that's in your house. Now, what I'm saying is, if you had nice warm floors, removing the carpeting isn't too bad of a thing. because I can have nice oak floors or whatever kind of flooring you like and be nice and toasty at the same time. Imagine getting out of your tub in the middle of winter and putting your feet on nice warm tiles. Oh, that would feel wonderful. And then besides that, we have the energy savings of one of the other benefits of radiant heat is the energy savings, because water can hold as much as 3,500 times the amount of heat as the same volume of air. And so as you see in this drawing here, an 8x14 duct carries exactly the same amount of energy as a 3/4 inch pipe filled with water. So you can see just from a space saving capability. And this is a chart that's it's a little mathy, but if there's any engineers online or something, they might enjoy it. Any of you architects, you'll find this fascinating. So the specific heat of water is 1. That means 1 pound of water, it takes 1 BTU to raise 1 pound of water 1 degree. For the same amount of air, it takes 0.24 pounds to raise 1 degree of air 1 BTU. Now, the density of water is 62.4. That means that a cubic foot of water weighs 62.4 pounds versus 0.074 for air. If you multiply the 1 times 62.4, obviously you get 62.4. And then if you multiply the 0.24 times 0.074, you get 0.018. Now these are the energy transport capacities of these two materials. How much energy are they capable of carrying? And if you divide the 62.4 by 0.018, you'll get 3466, or just about 35,000 times more energy can be carried by water than air. And because of that, we don't need these fan sizes that are so large and powerful, and the ducting can be smaller because all we need is makeup air rather than heating air as well. And we can also go ahead in this situation here and have our boiler heat our domestic hot water at the same time. And so now I have my nice 97% efficient boiler heating my domestic hot water versus 85% or 82% on a good day of water heater. So you get an energy savings from there as well, not to mention it heats much, much quicker. One of the other things you get is more usable space. You can put your furniture anywhere you want. So as an example, you know that you can't put your furniture everywhere in a room because you can't put it next to where the vents are, correct? So I remember one time my wife went out shopping and she came back with an etagere. I don't know how many of you know what an etagere is. I certainly didn't. I had no idea what it was. But it turns out it's this little cabinet that you put dishes in, and it's got glass on the front and a little drawer at the bottom that you pull out and store things in. So I said to my wife, I carried it in. I said, where would you like it? She said, well, I'd like it right on that wall over there. And I said, well, you can't, dear. There's a vent there. She said, well, that's where I want it. I said, well, honey, I can't put it there. There's a vent there. Well, she said, go figure it out. So I did. I took it out into the shop outside, and I cut the drawer out of the bottom so it would fit and the air could come where the drawer was. So we went to marriage counseling for a couple weeks, and we got that all straightened around. So we're doing fine now. But I learned a valuable lesson. You can't always place the furniture where you want it. Also, radiant heating is whisper quiet. There's no fans coming on, just a very small pump that uses very little amount of energy. So you get that benefit out as well. And you can get creative with your heating. In this application, the homeowner installed some radiant tubing underneath a granite countertop. Now, all of you know how cold those are in the winter when you put your hands on them. Now it becomes a heat emitter. It's actually part of your heating system. So you can use it for all kinds of applications. On the picture on the left, they put some radiant in a wall next to a large picture window. So you know that feeling that you get when you walk next to a plate glass window in the winter? Well, that's completely gone with that. Another one on the right is they took a shower and they installed radiant heating on the walls. Now you all know what it's like to lean against the outside wall in your shower in the middle of winter. It's really cold. Well, this heats it up. It becomes like a cocoon in there. So it's amazingly comfortable. So in in all of these things, I hope I've showed you a little bit of how the comfort, the quality, the efficiency of the system, Radiant provides a really good alternative to forced air. And I don't like to say it meanly, but I think forced air even sounds abusive, but that's just me. And I'll finish with this. You all, some of you might recognize this letter from the grades in school. Now this is a D. Now when you get a D for a grade, what does the D mean? Well, the D means you've done just enough to pass. You haven't done a single thing more. You haven't done just barely, you didn't flunk, you didn't fail, but that's all you got. My point is this, when you build a home to code today, that's a D home. That means you've done just enough to not fail, just enough so the house wouldn't kill you. And homes that are built just to code will not have the comfort curve that you'd like. And so I'm sure you're asking, well, how much does it cost to upgrade then to a Radiant system? Typically, it's about, if you're spending $3 to $5 on your heating and air conditioning system now, it'll cost you between $5 and $7 to do the same thing in Radiant. That's what industry standards are. So there are some that are more, but they're more elaborate, like when you put in geothermal. But a basic Radiant heating system with basic controls with a couple of zones in your house can go in from $5 to $7 per square foot. So it's not that far out of line. So I'm going to finish with that, and I think we're going to open it up for some questions. And I'd like to finish with the quote from Benjamin Franklin. It says, "The bitterness of poor quality remains long after the sweetness of low price is forgotten." That's such a good quote. So I'll turn it over for some questions and hang around if there are any.
Great, thank you, Steve. And yes, we did want to make sure to remind our audience to submit their questions via the questions box. Wanted to get to the first one, which is from Charles. He's got a project, and so we're going to kind of get into a little bit of project consulting here. He just wanted to know what's the most economical and efficient way to install Radiant floors. He said, we've got to remove the tile flooring, but they have complete access below the floor from the basement. They're going to be using a geothermal, a low temperature water to water heat pump as the hot water supply source. So can you talk a little bit about a situation like that?
Well, I got a little tear just hearing about the system you're installing there. I'm jealous. So if it were me doing it, they make extruded aluminum plates that fit right up underneath in your floor joists. And then you insulate, you put the, screw the extruded aluminum pieces in there, you snap the pipe into place, you insulate under it. And to me, of all the choices you get, that one would be the most cost effective and provide you with the best underfloor radiant heat, except unless it's a slab, down a concrete slab, which would be even better. But extruded aluminum. Now there is another option above the floor. If you want to go above the floor, most companies provide some kind of a track system that lays on the floor that you can put tubing in. And you can, for Upinor's products, you can go Google Quick Track, and it will. It's a 1/2-inch plywood with an aluminum backing, and it takes 5/16 inch tubing, and you snap that in and put it on top of your floor. So it's great for remodeling. You can put it on your walls. You can put it on your ceilings. If you wanted to remodel a garage, for example, you want radiant heat, put some Quick Track up in the ceiling of your garage, hitch an electric boiler up to it, and boom, got yourself a radiant heated garage. That's a great thing. I'd love to hear how that turns out in the future. I think my email's posted on there, steve.swanson@upinor.com. I'd love to hear how that system worked out. Or if you have any further questions, email me there.
Yeah. Well, he's got another question that we're going to get to in just a moment, but I wanted to get to John's question first. John wants to know your opinion on electric radiant floor heating.
It's radiant heating, so if you're, where I live, it's about 9 cents a kilowatt hour for electricity. And so it costs a little bit more to heat electric-wise, and it's similar to the toaster element that's in your toaster. If a part of it snaps anywhere, then you've lost the heating system. And walking on it, I've heard from other customers that over a period of years, if they don't grout it just right and do the subfloor just right, repeated walking on it could snap one of those elements and you'd have to relay it again. But it is radiant heated, and I think it just costs a little bit more to install. The good part about it is for a very small area that you want heated, just maybe your bathroom floor, that's a great alternative.
Charles had another question for you. He wanted to know if Uponor, who was the very generous sponsor of this webinar, does Uponor offer an option similar to warm board?
Yes, we do, and that would be the what we call quick track. So
Okay.
again, he can get back to me at steve.swanson@uponor.com, and I'd be glad to fill him in on the details and hitch him up with somebody who might want to get an opposing bid on that.
Yeah, and he said he was going to look into the quick track based on your suggestion there.
Okay.
So. All right, so here we get a complicated question, and it's one that I had too, Steve. So I'm glad that it came in from someone else too. Bill wants to know if a radiant system is more energy efficient than a forced air system, and I think it is. But where Bill's going with this question is this: he says he's lived in both kinds of, or in a house, in different houses that have both these kind of systems. He found that the forced air house had lower costs because they could adjust it at night and when they're out of the house, while radiant is much slower to respond to changes in temperature, and they just generally left it at the same temperature all day and night. And I've heard that criticism before, or some people have said, you know, the lag time and the temperature change. So is that something you can address for this?
Sure. There's different models of each one. Number one, for example, let's address the setback issue first.
Okay.
There are systems, like if you install Quick Track, the product we were just talking about a minute before, that's a very low mass product that you can set back in the evenings just as well. And then you can ramp it up, you can turn it, set it back, and it'll quickly cool down and quickly heat up when you turn the boiler back on again. So that's an option for that if you have that argument. Now, I would maintain that as most energy models will tell you, and including the Department of Energy and the study in Canada have shown, that over a long period of time, radiant heating over a longer period of time, even with high mass systems, is more cost effective. Now, it could be, and it may be just could be, if the system wasn't installed correctly, there might be an issue with the way that it's able to do that as well. But without seeing it, I have no way of knowing it. But modeling, engineering modeling shows that radiant heating typically is about 30% less than forced air. And that's why you're seeing a lot of commercial buildings are installing radiant heating and radiant cooling now, because they're the first ones that experience those large energy bills. And they're finding more and more that radiant heating is a better way of heating and cooling your building than using just air alone.
Well, I think as you showed, I mean, certainly from a delivery system, it is way more energy efficient. I've always been curious if there have there been any cost-benefit analysis done or any kind of studies like that done either by Uponor or the Radiant Professionals Association on
Actually,
some of those,
right now,
okay.
There's a case study going on in Canada right now that I don't know what the outcome of it is. I think it's still a couple years from being done, but they built two houses identical to each other side by side. They put radiant and forced air in both of them. And what they're doing is over a 5-year period, they're switching, or 6-year period, they're switching back and forth between the two to see if there's setting them all up the same. They have the same furniture in them, the same drapes, the same everything. But the study isn't done yet. So unfortunately, I don't know the results.
Okay.
That would be a good,
right.
When it comes back out, I'll be glad to come back and tell you what it says.
Oh yeah, that would be a fantastic webinar.
Yeah, I think so too.
Miriam wants to know, what's your opinion of low voltage radiant heating?
Miriam, if you could explain a little bit more of what the low voltage radiant heat is. It can't be resistive heating, I couldn't imagine. Tell me how that works.
Okay. We'll wait for Miriam's response on that. We're going to move on to Greg's question. Greg wanted to know, he's building a new concrete home. Is it better to embed the system into the concrete or place extruded aluminum above the concrete?
It's always better to have it in the concrete because you can drop the supply water temperature very, very low, and then that in turn makes your condensing boiler operate at a higher efficiency. So yes, installing it in the slab will nearly always give you a higher energy yield and better sustainability as well.
Gotcha. While we wait for Miriam to get back to us, I guess I wanted to throw another question to you. We were obviously talking about radiant floor systems. There are radiant systems for is it for the walls or for the ceilings as well? Can you talk a little about other placement of radiant?
There's a good case for, let's say, first of all, radiant cooling works better in a ceiling than it does a floor. So if you want a radiant cooling area, putting it in the ceiling works really good. Now, radiant, if I put those quick track panels on the wall, since they're only a ½ inch thick, I can put them up from the floor up to about 4 feet. So it looks like wainscoting or wainscoting, depending on how you pronounce it. And then put a little wood border around it, cover it with some light paneling or whatever you want. You get the same effect as the radiant heating as far as heating the area. The floors will not be quite as warm, but it'll eventually heat those floors up as well. Since it only gives up its energy when it hits something. It'll go right through the air and then give up its energy when it hits the floor. So eventually it will warm up, but you won't feel those nice toasty warm floors right away, but your house will heat with radiant heating for quite a bit less money and in the walls. So you could do that in the ceilings as well.
Okay.
Yeah, it's a great alternative. And then you can have any kind of flooring on there you want. If you want to put carpeting on the floor, you're fine, go right ahead, because it won't affect the performance of the radiant panel.
Yeah. Now, the carpet will still absorb all that stuff you talked about, all that undesirable stuff. But
isn't that something? There's some videos online that show microscopically what's going on inside of your carpeting, and trust me, you don't want to watch it. It's not, no matter how much you clean it, is a problem. So anyway, that's life.
Yeah, it's pretty staggering. So Miriam did get back to us, and she said as far as she knows, it's a grid system that runs off of low voltage electricity. It uses a thin flat cable. The company is called Step Warm Floor. So do you have any familiarity with that?
I've only seen it in one application, so I'm not an expert on that at all, and I wouldn't want to comment too much on it since I don't know how far it's embedded in there or how safe not safe, but how long those little wires would last before they break, because they're going to break eventually anyway. That's the problem. Like your toaster. Eventually, those little elements are going to break eventually. So anytime I shoot electricity through a piece of metal to heat it up, eventually it takes the tensile out of the metal, which then makes it brittle, and eventually someone will step on it or roll a piano across the floor or something with a high pounds per square foot, and once one part of it snaps, a lot of times you lose a whole section. So that would be my only.
Yeah, I like that analogy there, Steve, about the toaster, because it's an easy visual that a lot of people have.
Yeah. Yeah, but my toaster works really fine till the exact day I need it, and then by golly, that's when it goes.
Probably when you're hosting some family over or something.
Exactly. You got a big crew coming over. Sorry, no toast. Oh well.
We got a question from Daniela. She wants to know, have they made any progress with radiant cooling to deal with the condensation?
Oh, very much. That's a great question. Thanks for asking that. Actually, at the end of the day, there really isn't a condensation problem. It's a thermostat problem. If you have a thermostat that can measure relative humidity, which many of the thermostats can do today. You put that on the wall, and it just keeps the water temperature 2 degrees above the dew point. It will never condense. And since we're running such high water temperatures anyway for radiant cooling, you don't run 30-degree water to make radiant cooling. You run like 60-degree water. So hardly ever is it below the dew point anyway. And then if you put a thermostat in that measures relative humidity, you'll have no condensate at all. That's how these big commercial stores are all doing commercial applications of radiant cooling today. Almost all of them have radiant cooling installed now because it's so easy to use. One of the executives from a large chain of stores, I can't mention their name, they switched over to radiant cooling for that very reason, and they dropped the number of air handling units on their roof from 26 to 13 on every one of their new stores just by switching to radiant cooling. That's a huge amount of savings. So yeah. It works great, and all you have to do is keep it above the dew point and it will never condense.
Do some of those systems come with some kind of sensor that can sense the dew point and adjust accordingly, or is that something you have to manually control?
No, it's built right into the thermostat. It looks like a thermostat. You just have to look up thermostats that measure relative humidity, and they're all over the place. Okay. Honeywell has them. Okay. We have them. Everyone has them.
Okay.
And they're made right for that, radiant cooling.
Right, of course. Greg has a question. I know Warm Board is a competitor to QuickTrack, but can you speak about your thoughts on Warm Board?
Oh, I'd rather not.
Okay, that's fine.
You'd have to go compare cost per square foot and output based on cost, and there's some other things. And I'll let the customers do that. They're really quite good at it now anyway, so they're good at analyzing the two. Warm Board's been around a long time, and I know it's installed in a lot of places. And hey, they're radiant people like I am, so I'm always happy with the Warm Board guys. So I'll let the customer decide.
You know, my take on it all has always kind of been, the more important decision is, are you going radiant or not? Then at that point, you're kind of splitting hairs on which route you're taking, but you've made the bigger decision, which was to go the direction of radiant.
Correct. I think that's a much better way to look at it. Well put. Thank you.
Daniela wants to know, she's looking for a recommendation. Do you have a company that deals with radiant cooling in Los Angeles? Do you know anybody?
If you'll Danielle, jot me a note. I'll hit you up with our rep out in that area, and I'm sure they'll find a contractor out there that could do that. And if you do it in the wintertime, Danielle, I'll come out personally and take a look at it. In Los Angeles in the middle of winter, oh, I'd be delighted to go out there. Anything to get out of it.
You wouldn't have to twist your arm to get you there. Another question from John. We're going back to radiant cooling for a second here. Okay. Can the same system be used for both radiant and cooling? So I think he means radiant heating and cooling.
It can.
Says, well, yeah, because he looks at it as you're just adjusting the temperature of the water at the boiler, right?
Correct. Now there are some, if you want to design it for radiant cooling, it sounds like we're getting enough interest in radiant cooling. Maybe we need a webinar just on radiant cooling, just for that, in the future somewhere. But to answer his question,
it's timely as we're going into summer here.
Yep. So in the radiant cooling, cooling takes more to do than heating does. Because remember, I'm not creating cold, I'm removing heat. And that's a different animal altogether. So because of that, I'm going to want to use a little bit thicker tubing, 5/8 instead of 1/2 inch. And I'm going to want to put them 6 inches on center instead of 12 inches on center. and I'm typically going to want to have the delta T between the two of 5 to 8 degrees instead of the 10 degrees or 20 degrees that we run for radiant. So those are three things that are going to change. Then when you change it to those parameters, it'll do heating and cooling equally well. So you use 5/8 inch tubing, 6 inches on center, set the delta T to 5 to 8 degrees, and that'll run your radiant cooling. And it'll also do spectacular for radiant heating since the tubing is closer together.
So let's get a little more technical here, Steve, which I know you can certainly handle. John's follow-up question is, what if you're using the boiler to heat your hot water tank as well? But then Michael brings up a point, not me, but a different Michael, brings up a point about, can you just use tap water without having to chill it for the radiant cooling system?
Michael, you can do that. I think it's against the law in most parts of the country, since they don't want you running potable water through a cooling system. You may want to check with local codes to see if that's even allowable. But first of all, your water bill is going to escalate significantly after that, since you'd be running quite a bit of water through there. So there's some offsetting benefits versus cost there, I think. Then, in relationship to the heating the domestic water with a modulating condensing boiler, those will go down well easy enough to do just the domestic water in the summertime at still the high efficiency. And
okay,
still have
so you
the same. Sorry.
No, it's okay. So you can still use the same boiler that you're using to heat the hot water tank. You can use that certainly for the radiant system.
Correct.
But
That's
then
absolutely
if you're okay, but if you're doing a radiant heating and cooling system, what can you just talk about that? Okay.
Yeah, you'd need a boiler to heat the domestic water and the radiant, and then you'd need a chiller to heat or do the cooling. And you could either use a mechanical chiller, or you can get a geothermal unit if you have the room available. Very economical. And then, if you do that right, you can run your heating and cooling off from the geothermal. We have a friend of ours that put a system in out in South Dakota. It is a 2,300 square foot house, regular installation and windows, and he put geothermal radiant heating and cooling in, and with not a whole spectacular lot of extra bells and whistles, and his entire energy bill for the year is $250 for heating and cooling. 2,300 square foot in the middle of South Dakota, and we all know how cold it is there, and how hot it gets in the summertime. $250 a year.
That's usually people pay a month.
Oh, so, I'd like a bill like that.
That's amazing. So refresh my memory on this one, Steve, because I'm trying to remember if you covered anything about air changes per hour. And the reason I'm asking is because John had another question about you just need an ERV to move the air. And I'm thinking about it in the context of air changes per hour to be able to, if it's a new construction, to meet the energy code. So can you talk a little bit about that?
It depends, again, which part of the country you live in, what the energy codes are for that state. But again, the air changes per hour changes between forced air and radiant. Typically, their forced airs are designed at a half of an air change per hour. That means how many ever cubic feet are in your house, they want half of that air to change every hour. With radiant, it's a third of an air change per hour. Now, often you're able to accomplish that with something like a bathroom fan with a timer on it. I've seen that used many, many times. So it'll run 10 minutes out of an hour at 60 CFM and do enough makeup air to accommodate that. Now, the other way they have is they use what they call whole house dehumidification system with really tiny distribution piping going to the rooms. It dehumidifies air coming in from the outside, and puts it in the rooms as makeup air. And they use, I don't think the tubes are any more than about 3/4 of an inch. It's really quite the system. So it's called whole house dehumidification. So it dehumidifies the house and also provides air changes per hour. It's sort of like an ERV, except tiny little tubes, rather than a big massive distribution system.
Okay. Well, I don't see any other questions, and we're right here at the top of the hour, so I'm going to go ahead and conclude this one. Certainly, Steve, I wanted to thank you very much for sharing your time with us today and addressing all the questions and sharing all your knowledge and expertise. Really appreciate that.
Well, thank you. Thank you for having me on, Mike. I appreciate it, and look forward to being with you again.
Yeah, I also want to thank our audience for asking all those wonderful questions. And Uponor, thank you very much for your sponsorship of today's webinar. Now, we're going to see you back here 1 week from today. We're going to be discussing current residential construction practices using HERS and see how that lines up with the IECC and the ERI path. We're going to be joined by Jim Myers of the Southwest Energy Efficiency Project. He's going to take a look at a recent multi-state study that used data from the ResNet registry. And then we'll talk about how to leverage that knowledge to support energy code adoption, compliance efforts, and support builders to meet the energy code and exceed energy efficiency program requirements. And that webinar is going to be sponsored by PowerShift by NV Energy. So until then, so long everyone, and have a great day.